Hi. So if you don't know me, I'm Geraint. I'm a PhD student at the School of Mathematics under Vince. So part of my PhD, or a lot of my PhD, is playing with data, whether that's real world data from hospitals or data that comes out of mathematical models and simulations. And part of the analysis of that is visualizing, making plots. So I do all my plots in Python, and it's not just sort of academic people that use plots. A lot of you will know journalism use plots all the time. Management use plots all the time. And it's because plots are a really easy and quick way for the human mind to perceive data, relationships between data and numerical data. So to emphasize more about why we plot, there's a really famous set of data called Anscombe's quartet, which a lot of you might have seen before. So visualized it here. These four sets of data have nearly exactly the same summary statistics. So the mean and variance of X and Y, the correlation between them and the line of best fit are all the same for these four data sets. So before you visualize these data sets and you just do the summary statistics, you might think the same story is being told in all four data sets. However, as soon as we visualize, we can see that actually that's not the case at all. So visualization as a statistical tool can open up more of the story of the data than just summary statistics. That's one of the reasons why we plot. You can also see that we are not in Namibia, but I did give this talk at PyCon Namibia with Daniela, Nicolette and Vince. So it's just the same slides, don't worry. So, right, so before we can talk about planning a data visualization and how we go about doing that in Python, we kind of need to understand data and different types of data. So there are four main types of data. There's more types, but there's four main types. There's nominal, ordinal, quantitative, and relational data. So nominal data is discrete data where the values are mutually exclusive. So a value can't be, one observation can't have two values. This is also called categorical data, and the values have no numerical value. There's no order or distance between any of the values. So, for example, the answers to the question, what is your favorite book, would be nominal data, because you can't order books and you can't see any distances between books. Ordinal data then is the same, but the order does matter. So, for example, the answer to the question, how happy are you with a certain product? Are you unhappy, neutral, happy, or very happy? The order is important here. However, there's no numerical values to those categories, and the distance between those values is meaningless. It's unquantifiable. We don't know what the distance between unhappy and neutral is. It makes no sense. Therefore, we can't say that the distance between unhappy and neutral and happy is the same, because there is no distance. But then quantitative data, the values, the order is very important, but also the distances between the values are important. So this is your typical numerical data then. So for example, if I ask you what is your height, that would be quantitative data. This comes in two types. There's interval data and ratio data. Interval data has no concept of absolute zero. So for example, dates would be interval data, whereas ratio data has an absolute zero. For example, height, you can have zero height or negative height. And finally, relational data describes the relationships between discrete objects. But I'm not going to go too much into that. Why is this important? It's because the type of graphs you're going to be producing out of these is going to be determined by what type of data you have. There are certain charts that don't work with certain data types, and you can get some quite silly charts when you start mixing these up. So we need to really understand what data we've got before we can start planning our data visualization. Now, we understand our data. We can't just go and plot it yet. We really need to understand how we're going to represent this data. So there are lots of different elements and ingredients to a plot and a visualization of data. And this slide sums up a lot of research around that. So this has been taken from a brilliant talk by Professor Kennedy, which is from a data visualization workshop I attended, which some of you were also at. So she describes 6 different ingredients that are in a plot, elements of plots. That's position, length, angle, area, volume, and color. And the human mind and eyes can perceive subtle differences in these elements in different ways compared to others, and can pick up smaller differences better in certain ones than others. So this just summarizes a lot of research that went into psychology and stuff, and it's generally accepted that position and length is a lot more accurate for us to perceive than color and volume. So if we want to start planning a visualization, we're going to try and make it as accurate as possible because we want to pick out those details. But that doesn't just mean that every time we add a new variable, add another piece of information to a plot, we're just going to work our way down this graph. Because some of these don't play well together. So, for example, angle and position are kind of related, similar. Volume and color might not play well together because to be able to show volume in the 3 dimensions, you're relying on shading and stuff, so color might not work well with that. And also with volume, you've got the other problem of how do you show volume. You're going to try and do something in 3 dimensions or pseudo 3 dimensions, 2.5 dimensions, which has its own set of problems. So some people really like that, some people don't. So you have to decide, using these elements, what's going to go into your chart and how and why. So we know position, length are a lot more accurate than density and color, but because of this interplay, some of them don't work well together, some of them are not nice to work with. Color is still quite a popular one that a lot of people tend to use in their charts. Which comes to Python. So now we know a little bit of our data, and we know a little bit about what goes into a plot. How do we do that in Python? So there's this fantastic library called matplotlib. A lot of you have probably heard of that. And it's an extremely flexible library that allows you to really tweak an image to be exactly what you want it to look like. But because it's that flexible, it does have some drawbacks that a new person to the library will find it quite fiddly. There's a lot of options. There's things that are not quite intuitive because there's lots of ways of doing the same thing and stuff. So matplotlib went, hang on, to simplify all this, we're going to introduce a set of commands called pyplot. And pyplot is a set of functions and commands which tries to make matplotlib act like MATLAB. Now, I don't really know much about MATLAB, but what I interpret that as is this is beginner's matplotlib. This is if you want your quick plot, you can create really nice plots like this in 1 line of code, which is really nice. So here's a couple of examples of what you can do with pyplot, and you can see that to create a histogram, once you've imported pyplot, you just need to write plot.hist, and that takes in an array of data, and it produces your histogram for you, which is lovely. So step back a minute. We know we've got this pyplot that can produce all these lovely charts for us. What chart is correct, or what chart makes sense for our data and what our data types? So you can see the top row of charts here are all representing 1-dimensional data. We're just plotting 1 dimension of data, and they're all plotting quantitative data. That's the numerical data where there's distance and order are important. So a histogram takes your array of data and chops the range up into discrete intervals, and then just counts how many observations are in those intervals. And by plotting that, then you get this impression of a distribution of your data. A box plot is a visual representation of summary statistics. So a box plot will show you your median, it can show you your mean, it can show you your quantiles and your interquartile ranges and your extreme points. And that's all summed up in this image here. And then a violin plot that combines the two. So you get all those summary statistics, but you also get some sort of representation of what that distribution is as well. The bottom row here is showing two-dimensional data. So we've got showing the relationship between two different variables of the same observations. So the scatter plot in the middle is plotting quantitative data against quantitative data. And a line plot is doing the same. However, with a line plot, we are restricting that we've only got no more than one y value per x value. And then a bar plot, we are plotting nominal or ordinal data against quantitative data. So, like I said, understanding what type of data you've got will determine what sort of sensible plot you need. For example, with the bar plot, if you're going to be plotting nominal against nominal data, I've seen some people do that, that's a silly plot, it doesn't quite make sense. So, all of these are one line of code, and the one-dimensional data takes in an array of values. The two-dimensional data takes in two arrays of values where the observations are their position in that array. These can also take a variety of keywords such as plot color, font size for the axes, and so on, which can, even in one line of code, can still give you some sort of customization of your plot. But Matplotlib is a lot more powerful than that. It's a lot more powerful than these one lines to create a plot. So with Matplotlib, we have two objects. We have the figure object and the axis object. The figure object is your canvas. It's what you are painting on. It's what you're going to save. It's what you're going to show people. It's what you're going to print off. Your axis object is where all the information of that graph is. And the pyplot command subplots creates a figure object view, creates an axis object view, and binds them together. So when you're talking about your figure, it knows that that axis is on there. And then you can start building up your plot with lots of different elements of this plot by manipulating these objects. So, for example, if you want to add axis labels, for example, the y label here, you just take your axis object and use the method setYLabel. That will take in a string, and it'll add that to the axis, and then the figure will paint that onto your canvas. So that'll take a string. It'll also take a variety of keywords, for example, font size, position, color, and so on. And the same for the X label. If you want then your title, you just use ax.setTitle. So there's a lot of these things that you just set in the axis. Your ticks then. So the ticks are both the positions of your grid lines and where your date's going to lie, and also what is shown on your axis, the little numbers that come up on the side of your axes. So to set your ticks, ax.setTicks, that takes in a list of values where those grid lines and where those labels are going to be on the axes. And if you're using quantitative data, then your labels of your acted ticks are going to be just their positions. You're going to want to know what is that position and what data is being represented by that position. But if you're using ordinal or nominal data, then maybe having numbers and the positions doesn't make sense, because you might be plotting, for example, dislike, neutral, like, and so on. So then you can use set xtick labels, which will then take all the positions that you've set with x labels and apply strings to them. So you can relabel your ticks and make your plot more meaningful. So that takes in a list of strings or things with representations. And then if you're using color, and if you're using color on quantitative data, you're going to be using a color bar to as your legend. So a legend would be for discrete values of your color. For continuous values of your color, for quantitative data, you can be using a color bar. So you can add that to the figure. So this is a little bit different to the rest because you're adding that to the figure, not to the axis. That's because when you have more than one axis on your figure, you want to use the same color bar. So that takes in something called a mappable, which I'll show you an example of later. So that'll take all your information from your plot, from your mappable, and it'll apply the correct colour and scaling and so on to your colour bar. Then the data itself, you want to put that on your axis. That uses the same commands as the pyplot command, so ax.hist, ax.scatter, ax.plot for line plots, and takes in exactly the same as the pyplot. You take in your list of data or array of data. There. And finally, you can have annotations with ax.text. So that takes in a string of text and x and y positions to place that wherever you want on the axis. So I said that's just a couple of the basic things. There's more things you can add. For example, you can add a legend and you can manipulate the grid lines and so on. But these are some of the basic things to show you how you manipulate those axis objects. So that was one axis on a figure. The command subplots implies you can have more than one of these. You can have lots of little plots on your axis. So to do that, if I wanted a 2x2 array of axes on my figure, I'd say plot.subplots 2x2, 2, 2, and that returns a figure and an array of axes, and it just binded every one of those axes in that array to my figure. So then I have one axis, one thing I can save and one thing I can print out, but I now have a 2x2 array of plots on there. And to be able to access these, I just access them like any other Python array. So the array 0, 0 is this top left one. And then I can manipulate these as I did the single axes earlier. So I can manipulate the axis labels and axis ticks and the data themselves all separately for each subplot, which is quite cool. So now we've seen examples of how we can make these figure and axis objects and add things to them. I'm going to show you an example now of using that on some real data. So the real data I'm going to use it's come free on the internet. It's all the gold, silver and bronze winning times of the women's 200 metre Olympic finalists from 1948 to 2008. So my data looks like this, and I want to plot over time the trend in the winning speeds for each of the gold medals, and I want to know which one of those medals went to American athletes. So my code here and the plot that's getting produced by this code on the other side. So the first thing I do is create that figure and axis object and bind them together, and then with that one axis I can add 3 plots. So I'm adding 3 line plots here, and that produces the 3 lines you see here. Matplotlib already knows that these are different plots. You're not going to want them the same color, so it'll call them different for you. Finally, I'm going to show the plot. You can also save the plot and manipulate the plot however you want. So we've plotted the times against which year. I have now got bronze, silver and gold. I can use the keyword arguments in this command to change the color of the line. So for example, I can change the color with C to gold, silver and bronze. Notice I'm not just typing in gold, silver and bronze, because that might produce colors which don't look very good on a graph. So you've got to be really careful about what colors you choose. This might be a bit of a silly example because I wanted the colors to reflect the medals, but notice I did choose subdued colors. I didn't choose things that were too bright. And I also tried to get the colours to be all of roughly the same brightness, so one colour wasn't dominating all the other colours. So then I know the Olympics happen every 4 years, so I might as well have my ticks to represent that, so I know that my data points lie on where the ticks are. So I'm setting the X ticks to a list of the dates that I have, and because there are lots of dates, I couldn't quite fit them all in. I took the X tick labels and I rotated them vertically so I could fit everything in. I can now, as I showed you before, I can add X and Y labels to the X and Y axes, and I can add a title. And see, I'm using the keyword font size to make that font size bigger. Said I wanted to denote where the American athletes won medals, so I just manipulate the data to get a list of the X and Y points for just the American athletes. And I'm adding a scatter plot to this data, so I've had a fourth plot, x.scatter, with the X and Ys, and then I'm using the keyword arguments and manipulating those marker points. So I can change the line width, the size, the shape of the markers, and the colour. And that has produced these stars as markers for where the American athletes won. Now, I don't think that looks quite good enough, because you've got this overlapping of, they've decided to put the scatter points behind the lines, and it just looks a bit messy. So I'm going to use the keyword argument Z order. Z order determines the order in the Z direction. So I can then say that the line plots are going to go behind the scatter plot. So Z order 2 is above Z order 1. And that can manipulate where you are in the depth perception. So I can tidy that up a little bit more. And finally, I want to add a legend. So I can do that with ax.legend. And Matplotlib has automatically known where the four plots are, and has produced a little legend for me. But I haven't told it what to call these plot points yet. So I then, to be able to give these plots names, in the plots themselves, I can add a label. So I've added a label saying gold medal, silver medal, bronze medal, and the US athletes. And that legend has automatically picked up those labels and applied it to the legend. So you can produce this two-dimensional graph now with 4 plots on it using the code here. So I've mentioned one-dimensional plots and I've mentioned two-dimensional plots. How about three-dimensional plots? So I mentioned earlier that the 2.5 dimension sort of pseudo 3D, there's a lot of debate about that, so I'm not going to go into that. One of the common ways of showing the third dimension is by using colour. So I am going to talk about how we choose colour, how we choose these colour maps that get applied to quantitative data. So what I'm talking about now comes from a SciPy talk about choosing colour maps and what's important in colour maps and creating new colour maps for Matplotlib. It's a really fascinating talk, and a lot of colour theory and psychology went into this research. So to do this, you can do a little experiment. We've got 2 data sets here. So I've got one data set, which is a photo of a landmark of Windhoek, where I originally gave this talk. We're all still in Namibia, yeah. So this is a data set. It's a matrix of numbers, but that photograph has applied a colour map to that, and we know what that's meant to look like. We know what the underlying structure of that data is meant to look like. It's meant to look like this church. We've also got another data set where I don't know the underlying structure, and I want this visualization, this colour map, to bring out the structure of that. This is a 9x9 magic square, where all the rows, columns, and the largest diagonals all add up to the same number. So I don't know the underlying structure of one, I know the underlying structure of the other, and I'm going to apply various colour maps to this to see how these colour maps can handle the underlying structure of this data and how it represents that. So the most common, I say most common, was the most common. It was the default of Matplotlib colour map, Jet. We can see that's obscure in our church. You can see the light side or the dark side of the tower. We can see some of the trees in the foreground. It's been obscured by the colour map. Now, if something we know the structure of is being obscured, how can we trust its representation of the thing we don't know the structure of? So how can I know that that's my mind is perceiving the structure of that correctly? So we see that even the most common colour map has some sort of problem with it. But it's doing an okay job. You can see the difference between some of the values. Because there's so many colours, one thing we've got to do when we're looking at the plot, we've got to keep referring back to the colour bar, which is time consuming and is not very good for perceiving because there's so many colours. I don't know, does yellow run into green or does yellow run into blue and so on. So we can do a little bit better than that by having sequential colour maps. So these sequential colours, hot and cold, try to eliminate that going back and forth the colour bar. because we naturally know where the colours blend into each other. But these ones that came in Matplotlib, hot and cool, distort our church even more. Can't really see what's going on in the foreground and can't really see the church at all in this one. So again, I don't trust these colour maps to show the magic square at all. So I'm still not quite confident that that what I think that magic square looks like because of that colour map is what the magic square actually looks like. And some other ones that come in Matplotlib are these miscellaneous colour maps, which I can't really see the point of at all. We can't see the church at all, showing a totally different structure to that magic square. But maybe there might be some use to it, because it does pick out some details of the sky. It does pick out small details, but the bigger picture is obscured, totally obscured. So we can do better than these. So I said the sequential ones sort of was good because we didn't have to go back and forth the colour bar. So these monochrome sequential ones, black and oranges, these are doing well. These are representing our church quite accurately. So I'm quite happy with these two colour maps. So therefore I should be quite happy with how it's representing the magic square. So these are good colour maps. There's some slight drawbacks to these, is that if you're comparing across different screens with different resolutions, or if you're printing out and you know what printers are like with ink, these could be, because they're all one colour, these could shading could be obscured by different resolution screens and printing. But these are good colour maps. And finally we've got these diverging colour maps as well. So these are also doing a really good job with our church, and we can see some sort of structure with a magic square. These are not quite appropriate for the data we have, because how do I know that blue doesn't run into red? How do I know red runs into white? There's three colours there. I'm trying to find one sort of coherent blending. So this is because these are designed for a specific purpose, and they're designed for a purpose where your midpoint is meaningful. For example, a 0, where one colour is your positives, one colour is your negatives, and you can compare within the positives and within the negatives, but you can instantly see the difference between the positive and negative. So these have a specific purpose, so they're just not quite what we need for this data. So we can see the colour maps on offer are not doing a very good job. There's some that are okay, but they're not doing a great job. So a lot of research went into producing new colour maps, and we have what we call perceptually uniform sequential colour maps. And these are the new ones that are in Matplotlib. Viridis is now the default for Matplotlib, and you can see that these perform really well on the churches. They are sequential, so we can naturally know, we don't have to keep going back and forth the colour bar, we naturally know what goes into what. And these have a few other bonuses as well. The fact that when you print them in black and white, they still do the same job, they're still perceptually uniform, and they are fine for colourblind people as well, which is a really big bonus. So these are the recommended ones for use in Matplotlib, and Viridis is now the default, so I tried to stick to that one. So now we're going to have an example of building up a three-dimensional plot in Matplotlib, where we've got a function in x and y, and I've got my x and y values and these f values, and I'm going to plot a heat map of this and build it up. So I'm going to use the pcolor command. Pcolor is one of the ways Matplotlib can do heat maps. There are a few other ways with imshow and pcolor mesh, but this is one of the simplest ways of doing that. So I again produce my figure and axis objects and bind them together. And then I use ax.pcolor with this matrix of values z, and that produces what you see here. Notice that pcolor returns something what I've called HM. That is your mappable, which I'll use later. So we now the first thing I want to do is apply a sensible colour map. So I've applied one of the perceptually uniform ones, I've applied Inferno, using the keyword argument CMap. I'm then going to manipulate the ticks so that they represent the x and y values that I want. Pcolor the ticks that default with p-color are the indices of that matrix that I've given it. So that's fine if that's what you need. I didn't. I had values from -2 to 2, so I've relabeled everything. Also with p-color, each point here is a square. P-color puts the tick on the bottom left-hand side of the square, whereas this square is meant to represent a continuous domain, so I want the tick to be in the middle. So I've shifted everything by 0.5, that index, because everything index is 1. I've shifted everything by 0.5, and then relabeled all the ticks to be the numbers that I want. So I've got the ticks in the middle of the squares. I can then add a color bar, so I'm adding the color bar to the figure object. Again, that takes in a mappable, that mappable that was produced by the pcolor command, hm. So that color bar automatically knows what color map I'm using, and it knows the scale that should map it to the data I've got. See, this fig.colorbar returns an object, a color bar object, that is like an axis, which I can manipulate. So for example, I can then add set label to that color bar, just like I would set with the ax.set something. So I can set label, and I can add a label to that color bar so I know what that color bar represents. Just as I did before, I can add a title with set title and X and Y labels with X and Y. Now I'm going to want to show the grid, because the screen here is showing some white lines. When I save that as a vector graphics object, those white lines won't show. But I'm going to want a grid. So I have manipulated this ax.grid object. I've said I want the major axis ticks. I've chosen my color and my line style and so on. But that's not enough with a p-color to show the grid, because p-color saturates your axis. It totally covers the graph. So the grid is always behind the graph. So to be able to make this grid visible, I've had to set the heat map's Z order to be a special number 0. 0 means behind the grid. So if I set that Z order to 0, then the heat map will lie behind the grid, and I'll be able to see the grid and manipulate the grid as I have. So that's all I wanted to show. These are some of the libraries I've used. Thank the Phoenix Project for bringing me here to Namibia. And sorry? SciPy, yeah. So some of these, so Matplotlib is what I've mainly talked about. NumPy I've used for creating some of the arrays of data. Just makes things like a little bit quicker. But Matplotlib you can use pure Python with lists. Anyway, Seaborn is another library for plotting and doing some basic statistical analysis. I haven't used Seaborn in the slides I'm showing you. There's a link to a notebook full of examples of this here, and I'm using Seaborn there. Just Seaborn does this magic thing where if you import it without using it, it makes all your plots really, really pretty. So that just manipulates some of the internal settings of Matplotlib, which you can do yourself, but Seaborn's a nice library anyway for data analysis. So show them that there, and Jupyter is how I tend to do everything. So I wanted to thank everyone for that as well. And finally, there's some links here. I know the Matplotlib documentation is massive and filled with examples, which is really, really useful. But some of the APIs that I'm using, the summaries of the APIs are really useful and sometimes can be quite hard to find on Google. So I've got the links to them here, links to the talks that I mentioned, and some example data sets that I used in this talk as well. So thanks.
So Matplotlib's API sometimes gets a bit of flack, sometimes gets a huge praise. something, one bit of Matplotlib API that you could change?
Like a change.
What would it be?
The PyPlot is amazing. PyPlot is amazing that you can do one line of code, gives you what you need. But there's lots of ways of doing the same thing, which is not nice. If there was one way of doing things, so for example, when I was setting the axis labels with the figure and axis environment, I was using .set x label, but with PyPlot, you use .x label and you don't leave out the set. And that can just make things confusing when you're going from one domain to the other domain, even though you're using the same library. So I don't really like that, but it's still really flexible. Yeah.
Have you used a
Sorry, Noteplot. No, I haven't used that actually. What could you tell me more about it?
Well, what I used to do was basically
Okay.
is what used to be the standard
Okay, no, that's something I haven't used. I know there are other plotting libraries. I know people use ggplot as well, which plots like R does, and the Seaborn has all its own plotting function as well. Matplotlib is the first one I came over. It was the biggest one with the most documentation, so I tried to learn as much as I could of that. That's why I've settled into Matplotlib. Yeah. You need to pay for a MATLAB license.
As in, like, just within the list of so say you already had MATLAB.
So like I said, I haven't used MATLAB. I'm guessing that the fact that Matplotlib has this PyPlot that makes it act like MATLAB means maybe MATLAB's a nice interface to use, but I can't really comment on MATLAB because I haven't used it. But as I said, there's lots of things you can do with this. So these axes and figures are all objects which you just manipulate and pass around the place, which I find really nice. And you can pass them into functions and so on, which is all really nice. Yeah.
Can you go back a few slides to
Yeah.
pictures of the church?
Yeah.
So, if you wanted to show me a bunch of photographs of the church, so I took some photographs of the church, and you showed me that one in grayscale, i.e. black and white, I wouldn't blink an eye and think, oh, Geraint into black and white photography. If you showed me any one of the others, including the ones that you said are preferred, I would have said, well, that doesn't look anything like the church. And I think one reason for that is that we do have black and white receptors in our eyes. When it's dark, we see black and white, so that's very natural. But also there's this long cultural history of seeing black and white images and understanding that they represent things that are common in the world. It's not clear to me why the grey image there, or even the orange image, which you can see depicts a kind of wild sepia, isn't better than the ones on the next page.
Okay, so one of the criticisms that I've read about these monochrome ones is that comparing over different screens, comparing some screens or programs or even papers and printers sort of make things a little bit translucent, whereas that is just a translucent version of that. So it sort of just skews our perception of it because of that translucency. And when printing looks different to screen because of the different translucency.
So the additional colour is rescuing this risk of us from
Yeah,
this
rather than relying on the translucency to show what the data, we are relying on colour instead. Yeah.
And if I can ask a related question, does this depend? Does the choice of colour map also depend on what it is that we're really interested in? Because we get the outline of the church by
Um,
Would I be better off, you know, if I'm interested in the overall tendency towards darkness, you know, how much darkness there in that image, would I be better off looking at the grayscale image or maybe one of the ones on the next page?
I personally would say one of the ones on the next page, because when you say how much dark is in the image, you're using dark to mean something specific in this photo.
Say I'm not interested in the shape.
Yeah.
I want the total quantity of blackness.
Oh, I'm not sure. I'm guessing you then want to go into other statistics rather than just a visualization. The visualization could give you a lot, but you want to manipulate the data and look at other things. Myself, I would look at that, but I'm not particularly sure. But no, it's a good question.
The original question of there's not necessarily a best, but
Yeah.
best colour method. Would you say it does depend on what?
Yeah. Like for example, the divergent ones have a specific purpose, and these do the job quite well for the purpose of what I'm showing you. I'm showing you one image, but again, when you want to play with that, that's when the criticisms come in. Yeah. I've played with D3. I'm not great at D3, but I've had to play.
I was just wondering, would you use this over PyCharts for reasons?
So no, yeah. So I know D3's got specific purposes with showing things on the web and so on. There are ways of getting Matplotlib stuff into a web framework, and there's actually a library, if you like to work in Python, that you can write Matplotlib code, but it outputs D3, which is quite cool. But yeah, for static images and for myself, I work all in Python, so everything I do is in Python. It's nice to have producing my plots in Python too. Yeah, and Martin is good at D3. No, is that okay? Great. Thanks.
Does anyone have a writing talk they would like to give? Oh, fantastic.
Can I use that? Have you got an
That or this?
Yes.